Are there any other questions? Well, Julian, then that's the perfect introduction for yourself because you're the next speaker, and we will hear a follow-up on Fignition and what the Flash transition layer is about.
Oh yeah, that sounds good.
Yeah.
Yeah.
Go ahead.
Okay, I'll try and share it. So I'm sharing. Here we go. So you should be able to see Keynote, and okay, it started. So here we go. Yeah. So this is VDisk, a Flash translation layer in Forth for Fignition, and I'm Julian Skidmore. I got the usual stuff. And okay, so part of the introduction is like this. Sometimes it takes a long time to write software you always wanted to. So let's recap a bit. Fignition is a self-contained Forth computer inspired by the Jupiter Ace and also Andrew Holmes' Mark I Forth computer, which we've just seen in action. It's intended to be the simplest complete self-hosted computer I could design, simple enough to be fully understood by a single person and soldered together by a child. It has an AVR MCU which manages the devices it talks to, a Forth compiler, a keypad for typing programs, composite video out, USB for power, 8 kilobytes of RAM for the current user program, and half a megabyte or a megabyte of flash storage, because no one could ever need more than that. So today I would like to talk about flash storage, which implements a flash translation layer with garbage collection and wear leveling. But first, a bit of history. So I used to work for a company called Microcontrol Systems way back in 1992, and it was my first full-time embedded computing job. And what we did was we developed things like 6 megabytes. This isn't actually one of the cards, I couldn't find it. 6 megabytes solid state ISA cards for PCs, which pretended to be hard disks using a BIOS extension. So they could be RAM or EPROM or the very latest in non-volatile storage, 128 KB flash chips by Intel, which had one whole flash sector on them. Okay, the flash memory then was like the flash memory now, but a bit more crude. You could electrically erase all of it to ones, and you could write individual bits to 0. But our system only allowed customers to write to the disk once. And we did that by putting the FAT and the directories and caching them in the PC's RAM, and then the customer would copy all the files, and then they would get copied back onto the flash memory. So I was nearly fresh out of university and realized we could make a proper solid state disk using flash with the right data structures, and that would be brilliant because there were literally no standards for true flash-based solid state storage. If we had solved it, we could have defined the standard, and together we could have ruled the galaxy. But the company wasn't interested, and within a few years it basically went bust. It took 20 years and several design attempts later to develop my own flash translation layer, as they're called now, and it turns out we can develop simple ones in about 1 to 2 kilobytes of code, which is similar to a floppy drive controller. So let's look at the flash memory. SPI flash memory is random access. All we need to do is send a read or write or erase command followed by a 24-bit address, and then we can start writing or reading at that location. Although you can read from anywhere, you have to write from the beginning of a 256-byte page, and you can only erase from the beginning of a 4 kilobyte sector. In flash memory, erasing always sets the entire sector to 1 bits, and writing can only ever reset bits within a page to 0. However, on most flash memory controllers, you can do this multiple times. You can clear more and more bits anywhere within the page each time. And this means we can't treat flash like an old-fashioned disk. We can't overwrite a page with any new data we like, we normally have to write to a new page containing all ones each time. So what we want to do, if we want to have like a proper flash type disk, is that we need like virtual blocks. We could map our logical or virtual blocks to actual physical pages we wrote to, and the easiest way to do that is to build a virtual block table. As we update the virtual block table, we would update its entry point to the new physical block used. So for example, in this case, in the virtual block table, at the very end, we have virtual block 4, okay, but it's really pointing to physical block number 7, okay, and we can see that, for example, earlier on, physical page 0 had been replaced by another block earlier, so it's no longer in use, okay. But the thing is that...
Excuse me, I'm still looking at the first presentation page. Is that just me, or is...
Can no one see any of this? Is it just me talking and no?
It's just the first page, yeah. Oops.
Thank you, Keynote. I thought I was sharing. So
we see the presentation view of Keynote with the slides on the left and the first slide in the middle.
Okay, so you can see where it says updating virtual blocks now.
No, it's just...
You only see the first slide. You don't see any of the others.
Yeah, the first slide only.
That was
first slide on the list of slides, thumbnails.
Resume share. Okay. It says resume share. So you can't see anything. You can't see any of me changing anything.
We could see the first slide, and I think...
we thought all that was the prelude.
Can you see anything at all changing on the slides?
No. What? So why don't you stop sharing and reshare, and then we see if it works then?
Right. Okay. I'm really sorry about that.
Something bad happened when you pressed play, I guess.
Oh yeah, maybe it's a different window. Okay, right. Share screen. Okay. Right, does that work?
We have first slide full screen. Great.
Okay, can you see the blank screen? And now you can see Fignition.
All right.
Fignition,
awesome.
The printed circuit board populated.
Right. Okay, so I think I'll have to go back to that, and I'm sorry about just having to look at the original screen all that time. So, Fignition, self-contained computer. And what happens is that we know it's derived from this, and we know it's derived from the Mark I fourth computer. Kids have made it. They were really happy when they made it. And we see that Fignition is self-contained. It does all the things that you need. I used to work at Microcontrol Systems. We made 16-bit ISA cards, but they didn't really look like that. They were full of memory chips. And one of the things that we used to use was flash memory chips, which was quite new. And I wanted to be able to write some software that would make it a proper flash disk instead of just this kind of rudimentary system that you could only write once to. So serial flash memory is organized. You can access it randomly anywhere, but you can only write in 256-byte pages on Amic serial flash memory, and 8 pages of those go together to make a 4 kilobyte sector, and that is the level at which you can erase it back to ones. And when you write to it, all you can ever do is 0 the memory. So what we would like to do, because we end up having to use the new pages each time we want to write to some memory, we would like to be able to have like virtual memory blocks where we say we're like writing to page 3, and it allocates a new physical block to write to. So we can have a virtual page table, and as we update oh, there we go, that's how it works. That's how it starts off. And then we want to write to block 4 again, and this time we have to use page 7 because that was the one that was next available. Oh, that's good, nice bit of animation. And so the thing is that we can't actually store the virtual block table in the Flash itself, because that would involve changing the contents of the virtual block table, which you can't do for the same reason that you can't arbitrarily modify Flash pages themselves. So what you note, though, is that every time you have a physical page, then you're going to write it, you're going to write the virtual table entry into the next physical page. So you could in fact represent an inverse virtual block table so that each new element in that page represented the virtual block you were writing to in the new physical page. And from that, you could reconstruct the virtual block table that you want. And in this case, physical page 0 originally contained virtual block 2, physical page 1 originally contained virtual block 3, then physical page 2 contained virtual block 1, but later that was overwritten later on with physical page 5, and so forth. Some of these pages get overwritten, and in our case, as before, the physical page 7 now represents virtual block 4. So this means that because what we want to do is the data about the virtual page table represents metadata in addition to the actual Flash storage that we need. So we represent it in a different location. Okay, so as we modify Flashbox, the content area will get filled up. So what happens when we run out of Flash? Okay, and the answer is we perform some garbage collection. And garbage collection works like this. So if we imagine that this is a section of the Flash memory and some of these blocks are clean because they are still blue, and some of them have been overwritten and they are dirty blocks. And that happens all the way, say, to the end of the Flash memory. So the algorithm waits until we've only got 8 free pages left. And then what it does is it goes to the very first page that we started to write, very first sector that we started to write to, and we copy over all the pages that are in fact clean. And this leaves a few, in this case, pages 2, 3, and physical pages 2, 3, and 5, which have been overwritten later. So then we have 3 free left, and then we erase the first sector so that we can then carry on writing to the Flash memory. And what happens there is that as we do this, we continue to fill up the inverse virtual block table with new physical pages that we have written. So eventually what happens is that the inverse virtual block table will fill up too. But garbage collecting for that is much simpler. All we do for that is that we have 2 tables. So the first table is allowed to be filled up, and then it gets to the end, and then the second table, we allow that to fill up. And when we've got to the end of the second table, we know that all the physical blocks that were used in the first table will have been substituted with the physical blocks in the second table. And therefore, we can just erase the first table without having to be worried about whether we're losing any data whatsoever. And this is the summary of how it works. We start off with both tables not overwritten at all. Then table 0 starts to fill up, and then table 0 is full up, and we start to fill up table 1, and that eventually gets full up. And we can erase table 0, and then once table 1 has filled up completely, we can go back onto updating physical page entries on table 0 and erase table 1. And there we go, a complete algorithm. So the firmware itself for this algorithm can actually be put, I can put it on the whole screen. You can, it's quite tiny, but actually it's relatively short. It's about 300 lines of mostly forth code as it appears in the Fignition GitHub. It's not quite standard forth because it's sort of got various sort of quirks that allow me to compile it into ROM, but it wouldn't take much effort to convert this into something that was a standard forth. So, summary. VDisk shows how simple a Flash translation layer can be, and was the fulfillment of a project I wanted to do for the first company I worked for 20 years earlier. So thanks for listening to this. Does anyone have any questions?
Thank you. Thank you, Julian.
Oh, other questions? Please raise your hands or open your mic.
Oh, I'm so thankful that somebody told me that it wasn't really working correctly. I'm really grateful that I was able to correct that. Thank you.
Is the wear leveling handled as a higher level function, or is that part of your stuff?
It's just an inherent property of the simplicity and the crudity of how the Flash translation works. Because I just end up writing to the very end of the Flash sectors and then wrapping back round to the beginning, all the Flash sectors get written over at the same rate. So it does wear leveling as a byproduct of that. More sophisticated Flash disks, what they do is they wouldn't do it quite like I would, because it gets inefficient searching through all of the long list. I've just got a linear list. So what they do is they break up the Flash disk into smaller parts and try to balance the number of writes on each part. Because if, say, what typically happens is that certain parts of the disk will get written more often than other parts, so they have to balance it. But in my case, it's just a simple property of how the algorithm works.
Thank you.
All right. Are there additional questions? Doesn't seem to be the case, so thank you again. I really appreciate that.